Introduction. Aman, can you please come here? I want to ask you something. What happened today? See there. A machine is moving the scrap of iron and steel from the waste material. Yes, I can see that. But how is it possible to extract the desired material from the wastage? It is simple. Basically, it is an electromagnetic crane which works on the principle of magnetism. Its anchor is made up of an electromagnet. When electric current is passed through it, it behaves like a magnet and attracts only iron and steel from the scrap. Okay, I got the answer of my question, and I want to know more about this. Will you please tell me? Sure. Today we will study about the magnetism and matter. Definition. The phenomenon of attracting magnetic substances like iron, nickel, cobalt, etc. is called magnetism. A body possessing the property of magnetism is called magnet. The two centers of attraction in any magnet are called its poles and are named as North Pole and South Pole. The region around a magnet in which it exerts forces on other magnets and on objects made of iron is called a magnetic field. Bar magnet. A magnet in the form of a bar with magnetic poles at each end is known as a bar magnet. The main properties of a bar magnet are as follows. When a magnet is suspended freely, it aligns itself with one end pointing towards north of Earth and other towards south of Earth. Unlike poles attract and like poles repel each other. A magnet attracts magnetic materials. This attraction is maximum at the poles. Isolated magnetic pole does not exist. Magnetic poles always exist in pairs. A magnet can induce magnetism in substances like soft iron, cobalt, nickel, and various ferrous alloys. Magnetic field lines. A magnetic field can be represented by lines called the magnetic field lines. A magnetic field line is defined as the curve, the tangent to which at any point gives the direction of the magnetic field at that point. Magnetic field lines never intersect each other. The magnetic field is stronger in regions where the field lines are relatively close together and weaker where they are relatively far apart. Magnetic field lines are always closed continuous loops. Magnetization and magnetic intensity. The magnetic state of a bulk piece of material is characterized by its magnetization, which is defined as the magnetic dipole moment per unit volume. The magnetization depends on both the magnitude of the individual atomic dipole moments and their degree of alignment. Magnetic field intensity. It is defined as the ratio of the magnetic field in free space to the permeability of the free space. H is equal to B naught divided by mu naught. The magnetic intensity depends on the geometry of the circuit and the conduction current, but not on the medium. The total magnetic field in a magnetic material is due to the conduction current in the external circuit and the microscopic current developed in the material. B is equal to B naught plus mu naught M. It can also be written as B is equal to mu naught multiplied by H plus M. The magnetic field is also called the magnetic flux density or the magnetic induction. Magnetic flux. It is a measure of the quantity of magnetism, being the total number of magnetic lines of force passing through a specified area in a magnetic field. If a uniform magnetic field B acts perpendicular to the plane surface, then the magnetic flux through the area A is given by the product of B and A. If the magnetic field B makes an angle theta with the normal to the surface, then the magnetic flux is given by BA cos theta. Or it can be written as phi is equal to dot product of B and A. Magnetic flux linked with a closed surface may be defined as the product of the surface area and the normal component of the magnetic field acting on that area. Faraday's law of induction. Faraday summarized the results of his experiments in the following two laws. Whenever the magnetic flux through a circuit changes, an EMF is induced in the circuit, and it lasts only as long as the change in flux is taking place. The instantaneous EMF induced in a circuit is equal to the time rate of change of magnetic flux through a surface enclosed by that circuit. E is equal to minus differentiation of phi b with respect to t. The negative sign is introduced to indicate the direction of the induced EMF. The induced EMF always in the opposite direction of change in magnetic flux. If a coil of wire consists of n loops, each with the same area, then the flux through all loops is given by minus n differentiation of phi b with respect to t. Example. Let's take an example on Faraday's laws of induction. The magnetic flux through a coil perpendicular to its plane and directed into the paper is changing according to the relation. Phi is equal to 5t square plus 10t plus 3 meter Weber. Calculate the EMF induced in the loop at t, which is equal to 5 seconds. Let's see the solution. Given phi is equal to 5t square plus 10t plus 3 meter Weber, it can be written as phi is equal to 5t square and 10t plus 3 multiplied by 10 raised to the power minus 3 Weber. We know that E is equal to d phi by dt. By putting the values in this equation we get E is equal to t plus 1 multiplied by 10 raised to the power minus 2 volt. Now, substituting the value of t as 5 seconds, we get E as 0.06 volt. Hence, the EMF induced in the loop at t is equal to 5 seconds is 0.06 volt. Lenz's law and conservation of energy. Lenz's law states that the direction of the induced EMF or induced current is such that it opposes the change that is producing it. When the magnet is pushed towards the coil, the induced current produced will oppose the push of the magnet by creating a north pole on the face of the coil near the magnet. When the magnet is pulled away from the coil, the induced current produced will oppose the pull of the magnet by creating a south pole on the face of the coil near the magnet. According to Lenz's law, the induced EMF opposes the change that produces it. We perform mechanical work in causing the change in magnetic flux. So, it is the mechanical energy which is converted into electrical energy. Thus, Lenz's law is in accordance with the law of conservation of energy.